Hello. So I'll be doing some polynomials. Of course, I won't be able to cover entire polynomials in like one class. Polynomials is like a huge thing. I'll be mainly focusing on one idea of polynomials, which I like looking at roots of polynomials. So I'll like first define what a polynomial is, just for the sake of completeness. So, wait, this is not working. Not working. So polynomial p of x is something like this. And so on. Basically, it's like a function, which is a very nice function. And so in this, generally, we call polynomials as a real polynomial or integer polynomial. That depends on where these coefficients lie. These AIs are generally called the coefficients. And this maximum degree term is called the degree. Also, just because this term to exist, we assume an is not 0. And x to the n is the maximum term with the highest exponent. We can say whatever that. So n is generally called the degree. And if all the AIs are say integers, we call p is an integer polynomial. And I'll for short notation write this. If AI are say rationals, then I'll write something like this. And if AI are reals, then this, like as you can guess. Mainly, we will be working in real polynomials. And the main thing about real polynomials is that, or like in general, there's something called the fundamental theorem of algebra. I'm not writing the entire thing. Says that every polynomial has a root in C, which is complex numbers. So if someone doesn't know complex number, feel free to ask. And right now, if you don't know complex numbers, assume it's some universal set, which in this condition is true. Like every polynomial, you can find a root of it for any polynomial, even in like C. Like this means any polynomial in something like C of L. So just take this fact for granted. If you don't know complex numbers, if you know complex numbers, then this is true if you didn't know the fact. So I'll be mostly focusing on this idea of roots and how do you look at polynomials in terms of roots. So I guess I'll start with the problem and that will be the best way to explain. Oops, too tiny. This might be something that you might have seen, and if someone wants a hard or buffer problem, I can give that. But sorry. But if people haven't seen this, try this for some time and keep on telling all of your ideas because clearly I don't expect you to solve it in like 5 minutes. Just keep on telling any ideas there.
Can try think of it like functional equations and just put zero and some values to see how it goes. At
Yeah,
first.
that's a good idea. We can try some values. So
P2 equals
After
to
plugging in x is equals to 0, we get that either P2 is equals to 0 or P0 is equals to 0.
that's a great idea. So I'll write put these ideas there. Okay, 1 second. It's writing bad. It's having some issues. I think. Wow. English. So we put x equal to 0. So we get this thing. So either p of 0 is 0 or p of 2 is 1. Great.
now we can just case for all guys like we can put that if we can consider if we have 0 is 0, then we can put x equals -2 then proceed.
That's a great idea. That's a very nice idea. So if P of 0 is 0, then we put x equal to minus 2. We get P of minus 2 times P of 0 is equal to P of 4. But notice this part is just 0. So we get P of 4 is 0.
And since we can get infinitely many zeros, P has to be 0.
Correct. Now, how do we get infinitely many zeros from this? It's like for the sake of completeness.
Just put x equals 4 and continue.
So we put x equal to 4. We get P of 4 times P of 6 is equal to P of 16. So we now get P of 16 is 0. And similarly, now we put x equal to 16 to get P of 16 squared is 0, and so on. We now get infinitely many roots. So if P has infinite roots, it must be the 0 polynomial.
Okay, this I understood, but does the same argument work for any functional equation?
So, okay, still this part, we can do it for a functional equation. We never use P as a polynomial, right? This statement right here is not true for a functional equation.
Okay.
For example, like I'll just define it for the sake of any function, say any real function. Say assume f of integers are 0 for n is an integer, and f of x is equal to x for not integer x. Oh, I'm not sure if this satisfies the original thing, but like there are functions which can have infinite zeros, but are not identically 0.
Got it.
So I just remove. For polynomials, you can say that a polynomial cannot have infinite roots. So also another fact I'll try to add here is like a corollary of this. Corollary of this turns out that a polynomial P has at most degree P roots. So a polynomial P can have maximum its degree roots. So like basically just assume this fact for granted. And now if it has infinite roots,
Is there a polynomial that has lesser number of roots than its degree?
yes, sure. Like, okay, in complex numbers, in complex numbers, because this theorem, you can actually get like poly has exactly degree P roots.
We can just take like repetition roots.
Yes, I mean, we can obvious, that's what I was saying. The issue is something like x minus 1 squared has, like, technically it just has one root as 1, but we generally write it as 1 occurs with multiplicity 2. Or like, the polynomial is actually 2 roots, which have 1, but they're basically the same. I basically don't want you to worry about all of these things. Just assume that you can always find a root, and that's what basically matters right now. But basically, you can have degree P roots, degree P complex roots with repetitions allowed. For example, this thing can have repetitions allowed, but this will always have 2 roots. Real roots, on the other hand, can be like much lower. For example, x squared plus x plus 1 doesn't have any real root, but it has 2 complex roots, which are distinct. So I hope this was fine. And even if it's not fine, just don't worry about it too much.
Yeah. Okay.
Also, like, if you're asking any questions, prefer unmuting and saying, because chat can get like very crowded. But yeah.
Now for the second case, if we just put x equals 2, then we get p of 4 equals 1. And we can continue this.
Wait, slow down. In the second case, now second case is p of 2 is equal to 1. So we put x equal to 2. So x equal to 2 gives p of 2 times p of 4 is equal to p of 4. But p of 2 was 1. So, well, this didn't
Awesome.
really change. So what do we do now?
What we can do is, if we let assume like a p of k is 0, like k is a root, then p of k square has to be 0. And if like k not equals to k square, then it must have like infinite many roots.
Great. That is a good idea. So if k is a root, that is, we have p of k is a 0, then we put x equal to k. This gives p of k times p of k plus 2 is equal to p of k squared. So p of k squared is 0. And we can continue repeating this. But there's one thing. Okay, we can continue repeating this, that we can get like something like p of k to the 4 is 0, then it's square, then p of k to the 8 is 0, and so on. Now, can someone like actually give me an argument that this will not stop?
If p of k to the 2n is 0, then if we put x equals k to the 2n, then you get k to the 4n as well.
K to the 2 to the n actually you get, not 2n. But
It's like index.
yes, but can you give me an argument? Like, what if something is saying, like, what if something like this happens? K to the 2 to the 100 is actually equal to k to the 2 to the 50. Can this happen?
If k is equal to 1.
Or minus 1.
1 or
For
minus
k equals to 1 or minus 1, only two cases.
0 भी तो है.
Right. Yeah, so here this implies k is equal to 0, 1 or minus 1. But notice, this is assuming that k is real, right?
Complex numbers है.
Because if when you go into complex numbers, this actually has a lot more roots, right? Does that make sense?
Yeah,
Yeah.
2 to the 100 roots.
Yeah, it has like a bunch of roots, and so we can't actually comment this. But the idea is nice. So if we have a real root, then we can say for sure that it must be 0, 1 or minus 1. The case of 0 we just did. So it's either 1 or minus 1, right? But we might have complex roots. What do we do then? First of all, I want to point out something, that you can actually plug in complex values of x, and it's not exactly an issue, because this will turn out to be like an identity. Does it make sense? For example, something like a plus b squared is equal to a squared plus b squared plus 2ab. This is an identity, and this is true for all real AB. And it's also true for complex AB as well. So when you have something which is perfectly an identity, you can actually put in complex numbers without actually having some issues going on. So does this make sense? We can actually put complex numbers and there's going to be no problem going on. It intuitively does seem true, but just be careful is what I'm saying. Like, this is not always true, just to ponder upon it when you're trying to put a complex number in a polynomial thing.
Wait, but I couldn't get it why actually we are doing it, because x is defined for real only, no?
Exactly. The polynomial, we are only doing for real values, but just because it's an identity, as in like, if a polynomial satisfies this, you'll actually end up at something like an identity. Okay? If it's true, if something is true for all real x, it's a polynomial, it's an identity, it's true for all real x. It's also true for complex x. Does it make
Yeah.
sense? So that's the idea. So if you actually have something is true for complex x, you can put in complex numbers and it's totally okay. Right?
Okay, got it.
So it is intuitively true, but do ponder it, like whenever you're trying to do something like this, do think about it, that can I actually do it? But anyways, let's go.
By the
Yeah,
way,
go ahead.
one more thing I had to do was that suppose in that thing p of x plus 2 times p of x equals p of x square. what if we put a value of x such that x square equals x plus 2? So p of x plus 2 and p of x square will cancel each other. Then we will have a value of p of x that will be 1. So we can just put it back and we will have some equality, I guess. Does this work?
That is a great idea. Let's try that. Let's try that as well. So we have another idea. What color as well? So one idea is trying to like force cancel things. So trying to find a solution to this, let's call the solution of this alpha. So then we put x equal to alpha. You get p of alpha times p of alpha plus 2 is equal to p of alpha squared. So either
Right.
p of alpha squared is equal to 0. Yes, someone was saying something.
No, it's
So we get this again, right?
Yeah, p of alpha square is 0, just put x equals alpha square and you are done.
Are we done? If you put x equal to alpha squared,
Oh, right, complex. Okay.
we need to still get that argument of complex numbers going on, right? But like okay, in this case, you are actually done if p of alpha squared is 0. Okay, so I guess let's do the complex number idea. Let's do the roots idea because that was giving us a bunch of roots as well, right? Now, the issue with that idea is what's happening is we might cycle back. If we don't cycle back, we clearly have infinite roots, right? Does it make sense? Like,
Yeah.
you're forced to cycle back. And if you're forced to cycle back, what is exactly happening?
We are having finite roots now.
We are having finite roots. So can we comment something about k?
And that 0, 1 or minus 1.
But that's for real k. For complex k, this is something general that we can comment about.
powers of iota, I believe.
Okay, I get what the idea you mean. Powers of iota are close to like roots of unity.
Yes, yeah.
Yeah,
That's
exactly. K must be a root of unity. Okay, if you don't know what a root of unity, that's totally fine. This is a key idea that I actually wanted to say. Is whenever you have something in a complex equation or like something which has complex numbers in it, a very, very nice idea is actually take absolute values. So an absolute value of any complex number is a real number. Just assume this is true. So like absolute is some real number. If someone doesn't know what complex numbers are, just assume this is a real number. And there is this very nice property that is true. This is all I want you to keep it in your head about absolute value. And this is all that we use. And this. That's basically all we care about. So assume it's something which maps complex numbers to real numbers, and multiplication is very nice. Addition is also like we have some nice inequality. Okay, so why is this useful? It's because if you look at this equation, and if you take now absolute values on everything, so this is just an example. You can do this more generally as well. But you have something like this going on. Now, notice, I'll just go slightly towards the right. Notice from this guy.
One second. So we had k to the k to the 2 to the 100 and k to the 2 to the 50 at the roots, right?
Yes.
So
The
why are
issue
we?
is the issue
No,
is okay. This is an example. I'm just doing an example. What might happen is like when you're repeating this procedure of going from k to k squared to k to the 4 to k to the 2 to cube and so on, you might end up cycling back. Like say you reach 2 to the 50, then you 2 to the 51, and so on at 2 to the 100. It might happen that k to the 2 to the 100 is exactly the same as k to the 2 to the 50. So when you're doing this operation, you're only actually just getting finite roots and not infinite roots.
got it.
Does that make sense? Great. So this is just an example. In general, like some two things are equal, we can do the same argument. Doesn't really matter much. Okay, this is true. Like mod x squared is mod x squared because multiplication is very nice, and basically you can take out of all of the exponent. So this is look something like this. Now, mod k is a real number. So now our fact is still true that mod k is either, okay, also mod k is positive, non-negative, whatever. So mod k is either 0 or 1. Brilliant. 0, it's only 0 for 0. So if it is 0, then k is equal to 0. We've done that case, right? So now we get that mod k must be 1. Very nice. So does it make sense? Like, this idea is actually very useful of like taking absolute values. So right now, is there any questions till now?
Can you please just give a quick review of what absolute value was? I forgot it.
Okay, I'll just do that. Okay, for people who know what complex number is, absolute value of a particular complex number is just this thing. What I want you to think is like absolute value of any complex number z is something non-negative. It is 0 if and only if the original complex number is 0. Second, if you multiply two complex numbers x and y, their absolute value is just the product of the absolute value of x and y. Third, basically the most useful, I guess, is something called the triangle inequality. The absolute value of the sum is at most the absolute value of x and the absolute value of y.
Wait, how are they calling this a triangle inequality? How do you know that they are from a triangle?
I'm sorry, what? I'm sorry, I couldn't get the question. What were you saying?
No, like this one, how is this a triangle inequality? I'm just asking that.
Okay. I really didn't want to do this, but if you look at the complex plane, this mod x or absolute value of x represents in some sense the distance from the origin to x.
Yeah.
So I hope you get what I'm trying to say. Triangle inequality. This length plus this length is actually greater than this.
Got it, got it.
If you don't get what I said, please don't think about it. Forget it. Assume this fact is true. Prove it algebraically for a bad bit.
Now it's clear, yes.
Now it's fine. Great. Brilliant. But now we are still not done. We have still some issues. What we have proved till now is that all the roots of p have modulus 1. Okay. What do we do now? I'll just rewrite the equation.
The real x must be 1 or -1 and the complex x lie on the unit circle. But I don't know if there is a good property which we could use to do something.
That is perfectly correct. That all of the roots lie on the unit circle. But there are a lot of polynomials that lie on the unit circle, right?
Yeah. Like
And not every polynomial works. So we need to extract some more information from the problem. If you notice, we've only been using x and x squared, right? We found that if k is a root,
should we put x -2? Or
why not? Like, just write everything and just try everything that comes to your mind. So let's try putting k -2.
equations now?
I'm sorry, what?
This is starting to seem like functional equations now. You're just trying random stuff that you find something and then
Like, a very, very useful idea in functional equations is like literally write everything that comes in your mind, and that will work. Okay, we shall not ponder upon functional equations. But okay, we found something more. That if k is a root, so is k -2 squared. Brilliant. Now, any ideas? So we generated a different root this time. What do we do now?
We can say like k minus 2 is also a root of unity.
Correct. Perfect. Great idea. And we said, like, exactly, I just explained what he said. It's like all roots of p have absolute value 1, right? So absolute value of k minus 2 squared must also be 1.
Yeah. Which is equal to the absolute value.
Which is equal to this. And
Yeah.
because absolute value is positive, this implies the absolute value of k minus 2 is also 1. So absolute value of k is 1, and absolute value of k minus 2 is also 1.
And thus k must be only 1.
Precisely.
Yeah.
This implies that k is actually just equal to 1. I'll explain this. One way is to do this algebraically. Another way is to do an inequality, which is maybe you can do something like this. And because equality holds, there must be, like, k must be 1 because okay, if equality holds, they must be like in a straight line. X. Whatever. Or another nice proof is the unit circle, looking at things geometrically. So we know k is in the unit circle, is somewhere there. And what is absolute value of k minus 2? It's the distance between k and 2 here. And we want this to be 1. So we have 1 here and 2 here. But we know that this distance is 1. This distance is 1. So any other distance basically is like greater than 1, right? Does that make sense?
Can you repeat this once?
Okay, I'll repeat this. So k we know lies in the unit circle, right? And we have the number 2 is something here. The absolute value of k minus 2 is this distance, like the distance between 2 and k. Now, we want this distance to be 1 as well, right? Does that make sense? And the set of points that distance 1 from 2 is also like a circle, right?
Okay,
Is
okay.
K a, is K a coordinate?
K is like a complex number. If you don't know this complex number stuff, forget it. Do this algebraically, okay?
So
Like,
K will be the intersection of both the circles, so it will be 1.
yeah, precisely. Do this algebraically. That's a better way, no? If k is equal to a plus bi, then absolute value of k is equal to 1 implies a squared plus b squared is equal to 1. Absolute value of k minus 2 equal to 1 implies a minus 2 squared plus b squared is equal to 1. If you subtract them, you get a squared is equal to a minus 2 squared, which means a is equal to 1. You can prove this is easy. And that would also imply b is equal to 0. Great. So we got that. All roots of b must be exactly 1, right? So what should the polynomial p be?
X minus 1.
Precisely. But what if it's x minus 1 squared? It still has all roots 1. And it satisfies as well.
Just like
So,
x minus 1 to the n works.
yes, precisely. X minus 1 to the n. But you also have a constant term here. All of these polynomials still have roots 1. Now,
For
as
the
every FE, we must check that this is a solution. So we go back to where we started. We check if this is a solution. We check kx minus 1 to the n times a x plus 1 to the n is equal to a x square minus 1 to the n. This means a square is equal to a. That is, a is equal to 1 because we are assuming a is not equal. Correct? So the only solutions are p of x equal to 0 or p of x is x minus 1 to the n. Are there any questions? If there are any questions, feel free to ask. Is it like fine for everyone?
Clear.
Okay, great. So I'll just recap the idea of the proof. So the main part of the proof was finding a root and then trying to generate a lot of roots. Every polynomial has finite roots. Our aim is to just somehow generate infinite roots and get us some contradiction, or we get that p is identically 0, or p is a 0 polynomial. We first tried to do this, and we got that all roots of k are 1 by using a very nice idea of taking absolute values on equations which have complex numbers in it. Then we tried to use the equation to get another root which is called absolute value 1. These absolute value details are boring. If you didn't understand it, assume this is true. The main idea of the proof we actually got is that looking at a root and trying to generate a lot of them. And then trying to like hope that they're infinite. If they're not infinite, we need to do something more. So great. I hope the idea was fine.
Can you, in that part where we actually, when we found that k minus 2 whole square is a root, so we let its absolute value 1 because ultimately we were also again going to into that cycle thing. That's why.
Yes, precisely. We first started with starting with any root k, and then we showed that its absolute value must be 1. Otherwise, p is just 0, right? Because we can just always keep on taking the square and generate infinite roots, right?
Okay.
So all roots of p have modulus 1. And just because k minus 2 square is also a root, it must have modulus 1, right?
Yeah, got it.
Good. If there are any other questions from anyone, feel free to ask. Oh, there are no questions, and I'll move on to well, this might seem some integer problem, but it's not very clear. Okay, we need to find all pairs of integers a b so that there's a polynomial p, so that this product is something of the form this. So basically, we have something like this one. So before this problem, I'll actually say something now. And each ci is equal to 1 or minus. So this is basically saying something like this. Some polynomial a of x and some polynomial b of x. We have that a of x divides b of x. So as you would expect, as division works in integers, if we have some integer a divides b, this means that b is equal to ac for some integer c. So this thing means the same. But The idea is, as you remember, that there were different classes of polynomials, right? We had integer polynomials, we had rational polynomials, and we had real polynomials. So this division depends on, in some sense, which class of polynomial is working. So if you're working on integer polynomials, then we must have, as you would expect, c of x as an integer polynomial. Similar with rationals and reals. We look at the part where it's real, even though the problem right now says it's integer. But let's look at the part where it's real. The main idea is what you'd want if it is then like c of x is a real polynomial. Then you actually just want to show that all roots of a actually are also roots of b. Does that make sense? Because if you look at this equation, if you put x as any root of a, we must have that x is the root of b as well. And this is true for all roots, even with the roots which have repeated multiplicity. Because like if a of x is something like x minus 1 squared, and b of x is something like x minus 1 cubed, you can't really put 1 twice into an equation, right? But if you want to show that some polynomial like which has repeated roots divide another polynomial which has repeated roots, you want to show that the number of times of that particular root occurs more in B than it occurs in A. Does that make sense?
Okay, so the roots of A are just a subset of roots of B. That's what you mean.
Exactly. Counted with the number of times a particular root repeats. So is this fine? Is this like idea fine? Great. Now try the problem. And again, any idea that comes to you, feel free to. Yeah.
From this, can we definitively say that the degree of p of x is n minus 2? Yes, sir.
Yes.
Okay.
Does P have to be 1 or minus 1?
P is a polynomial. Oh, are you
I
talking about
mean
B?
small b, small b.
That is correct. Do you have a proof?
I mean, I don't have a formal proof, but I think, constant terms multiplied would have to give an integer, and
And that's
since it has to be 1 or
precisely the
minus.
formal proof as well.
Okay.
That is correct. So I'll just rewrite what we had. X squared plus ax plus b times p of x is equal to x to the n plus blah blah blah. Okay, we'll think about blah 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 later. You have a plus c naught here, and each of the ci's are 1 or minus. So what he just said is identical to saying put x equal to 0. This means b times p of 0 is equal to c naught. Looks like c6, c naught. And notice p was an integer polynomial. So we have integer. I'm sorry, I couldn't hear what you were saying.
B must be plus minus.
Yes, precisely. And this is equal to 1 or it's minus 1. And the product of two integers is 1 or minus 1. Well, both of them must be 1 or minus 1. So b is 1 or minus 1. Great.
Also, the leading term of P must also be 1.
Perfect. So now this idea was basically looking at constant terms. And you can actually look at any degree term. It's not that like you take the linear term here, multiply them. But what I'm trying to say is when you expand polynomials, something like x squared plus ax plus b times x plus c, say for an example, then you can directly multiply the constant terms as the constant thing. For the linear term, we'll actually look at b and x and ax and c. And they'll look at ax, acx plus bn. So this is actually the entire linear term. So when you're looking at a particular degree term, you try to match terms which have the same degree, multiply all of them and add them. And that's going to be the resultant degree in the product. Or like the same coefficient term in the product, not the degree of x to the some smaller. So we can do this for the largest term as well. And just because the only thing that will sum to the maximum things would be x squared here and x to the n minus whatever thing here. And it must be x to the n. So as someone said, we can say that this must be x to the n minus 2 as the largest term. And if you look at these constants, this is 1. This is something. And this is 1. So 1 times something is 1. So something must be 1. Great.
It's like you can just tell this argument that for anything, like any power of x from n minus 2 to 3 or 4, they will have coefficients for p of x.
They will have coefficients. What do you mean like that? They have positive coefficients or something. I don't get
They will have coefficients 1 or in the set 1 or minus 1. That's what I'm saying. Vaguely.
Of p.
Of p of x, yeah.
Are you sure that is true?
Like. Oh no, it's not.
No problem. Take it.
I think taking cases on B with plus and minus 1 like would help narrow down cases of A if you just analyze them separately.
Yeah, sure. Fine. Let us do that. So we have one case is b is equal to 1. And we have another case b equal to minus 1. So let's start with b equal to 1. So we want x squared plus ax plus 1 times p of x.
I'm thinking of using the coefficients of x square in both the sides.
Okay.
So now if we actually just multiply it by 1, like a bit of like we leave the left hand side with x square plus ax into px and take the px to the right hand side, then we get that the coefficients of right hand side will be either minus 2 or they will be okay. Okay, that's not no.
I think A is also plus minus 1.
Yep. How do we prove that?
Uh, uh, Take the coefficient of x in the second product polynomial to be c, then we must have AC plus minus 1 equals plus minus 1.
1 second, 1 second. Let's just say right p of x is equal to say something like what's yi x to the I, okay? I is equal to 0, 12 minus 2. So the coefficient of x looks something like y1 plus a y0 is equal to c1, right?
Yes, and c1 is plus minus 1
Yes.
and y0 is also plus minus 2.
Correct. But the issue is a might be something weird, right?
There's
We
an-
can't actually say that y1 must be 1 or minus 1. It might be true, but we can't say it right now, right?
Yes.
Right.
I was-
Yeah, no problem. Okay, I'll give a hint. Let's start looking at roots. Essentially, we want this polynomial x squared plus ax plus 1 in this case to divide some polynomial which has some restrictions on its coefficients, right? Like coefficients are 1 or minus 1. So let's start by picking a root alpha. alpha is root of x squared plus ax plus, let's say 1 for now. If b is equal to 1, we're taking the case of b equal to 1. Then we have that alpha to the n plus cn minus 1 alpha to the n minus 1 and so on. C1 alpha plus C naught is equal to C. Right? Because, or like in easier ways, just put alpha in this equation. Like we have this is 0, so this guy must be 0. Great. So we have this is 0. What do we do with this now? Notice alpha might be a complex number as well. It's not necessarily real. Might.
We also know like alpha square plus a alpha plus 1 equals to 0. So what we can do is like reduce the degree of n to a lower number.
Right. Right. That is correct. So, okay, this is like minus of this. And then we have like alpha. What you're saying is like this. So minus the alpha square minus alpha, which is equal to a times a alpha plus 1 is alpha a square minus 1 times alpha. So this is a great idea, and this is actually useful in another problem, which I will come to. But there's one issue with this idea right in our problem now. Is that if we try to use this idea, we lose this information on the coefficients being plus or minus 1, right? Like when we reduce something linear, there might be like some block where we are not able to, actually grasp the true information that these things
Yeah.
have. Like that is one issue that's happening. But otherwise, this is actually like a great idea, and this is used in another problem as well. So I was planning to do. So this is, I think I'll just give it away because this is a very nice idea and it's actually used in a lot of problems. So what we do in this is we again use the idea of taking the absolute value. Now we write alpha to the n. I'll also explain why we'll write this later. So we'll isolate the term alpha to the n. And then we look at absolute values. So we will just take these. Look at these absolute values. So this is equal to absolute value. So big absolute values are already something. Cn minus 1 alpha to the n minus 1 plus so on till C1 alpha plus C naught. And now we use the triangle inequality. This is at most, I can take terms out individually. And now because multiplication is very nice, I can write this.
The absolute value of all coefficients is 1.
Exactly. And now because all coefficients are absolute value 1, this turns out to be this. Actually, it's like equality. Like this. Yes. And this originally was also equal to this.
Yeah, so if we have alpha modulo of alpha as a real number, then that to the n is less than or equal to the sum of all the terms before. So
Yeah. Yeah, right. So let's actually write this in a neater way. Let's call alpha absolute value of alpha is some r. Okay. So what we got is that r to the n is at most r to the n minus 1 plus so on till r plus 1, right? We
So
want
R
to
has
get. Yeah, go ahead.
R has to be less than 2, I guess.
Perfect. So I'll explain this. This is equal to r to the n minus 1 by r minus 1. So, okay, you can like check it by multiplying. Believe me, this is true. So we claim like r is less than 2. So if r were bigger than 2, this implies r minus 1 is actually, yeah, if someone has a question, feel free to ask. Was that by accident or like you had a question? Okay. So we get a contradiction. This is tiny, no, kind of like a lie I was doing here. I actually needed r greater than 1 as well, or less than 1, but you can figure out the proof. Like technically division and multiplication with inequalities with negative numbers can cause problems.
Can you just move a bit?
Yeah, so basically, this was the main thing. And the reason why we did this is, yeah, go ahead.
I was asking what was the motivation behind taking the
Exactly. The motivation behind taking the absolute value is kind of like, okay, this is kind of like a very common trick in some sense. Like you'll be used to it a lot more. So I can explain the motivation of why we want to isolate the first term. So generally, I'm taking absolute value and bounding is, you know, kind of like an idea which is going to be used so many times that you should just keep it in your head and just keep looking for it rather than have a strong intuition about it. But on the other hand, one intuition about this is like the coefficients are very peculiar, right? So, and the questions are very small as well. That is either 1 or minus 1. So one example is like if you look at the number 2, number 2 can like never be a root, right? Because 2 to the n is already like way much bigger than any plus or minus linear combination in the previous guys.
Yes.
So what you expect is like large roots can't really, like large numbers can't really be roots of this thing. Does that make sense?
Yes.
In some sense, that the reason they can't be roots is because the biggest term, x to the n, can become like much larger than anything before that it can actually make any linear combination. Does that make sense?
Yes.
So that's what we did basically. We isolated the biggest term, looked at the remaining things, and tried to use triangle inequality and like bounded it to something which was hopefully smaller. Does that make sense?
Yes.
I hope that's some good motivation. But again, you can motivate this, but I'd actually want you to keep this idea in your head and just look for it as well. Okay, great. Are there any questions with what you've done till now? We haven't solved the problem, yes?
And I've got a question with like, why did we claim R to be lesser than 2? Like, why 2? Why not like 1? What's
Yeah,
the motivation behind 2?
and 2 is like just a number which makes this smaller, which makes this bigger than 1, right? Because this inequality is actually false for numbers less than 2. Like if you look at say something like 3 by 2, this is actually false. Like, I mean, this is actually true, not false. This is actually true. So we don't
Oh,
really
wait,
get
R,
anything.
R is like an integer, right?
No. R is like a real number. The absolute value of complex number is any real number, a positive real number, not an
So,
integer.
but what will we do with R less than?
We will do something. Wait. Anyways, let's not look at R less than 2, what will happen after the solution. Is the point till R less than 2 fine? And like absolute value of a complex number is a real number. Because complex numbers, okay, you know what? I'll just tell what a complex number is. Complex numbers are the form a plus b I, where I is some magical thing. I is like square root minus 1, and a and b are real numbers. So the absolute value was something like this, which is also real, right? So great. Are there
Yeah.
any questions you want to do? I hope everything is perfectly fine. If there are any questions at any point of time, feel free to ask. Okay, anyways. So we got r is less than 2, which means any root of whatever that blah 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 thing was has modulus less than 2. Why is this useful? It's just because we exactly know the root, what you want to work on. We have our polynomial x squared plus ax plus 1 in this case, as we'll do the case of -1 as well. And we literally know the roots of this polynomial. This polynomial has roots looking something of the form this. If you don't know how this came, believe me. If you know, that's great.
And
So
we
what
know
we know,
these roots are of
I'm sorry.
these roots are the roots of that greater
Yes,
polynomial, so the modulus will also be less than 2.
exactly. And just because he said if you pick any root of this is the root of this big guy, and this big guy has absolute value, all roots with absolute value less than 2. The absolute value of this guy is less than 2. Now the problem is in so much of mindless algebra. So
You just open the modulus with like
yeah, because now a is an integer, you can say this is true. Like, I don't want to do this right now.
yeah, it looks very
Uh,
bad.
Yeah. Can I like skip? Okay, okay.
Now we will have to put a is equals to x plus b x plus yi.
No, a is an integer.
But A is positive or not?
One
So
sec.
a is integer.
A is an integer.
Okay, just an integer. Okay. Yeah,
Yeah.
it's a pain. It's a pain.
Yeah, like right now it's just some, sad algebra. Like,
By the way, can't we just, as square root of a square minus 4 is just positive integer? No, not an integer, just positive. So can't we just
yes,
take it out of modulus?
not necessarily. Yeah. Okay, wait, we might be able second. Okay, a might be much more negative, right? So like say -5 plus 1 modulus is 4. But like we can't technically take it out.
So it's okay.
Anyways, basically right
So
now it's just some algebra. Okay, I'll just do it for the sake of completeness. If a is greater than 3, a plus square root a square minus 4 is greater than 3 plus square root 5, which is bigger than 4. Right?
so A doesn't.
So a must be less than 3, less than at most 2. And now we need a lower bound as well. Very sad.
If A is less than minus 3, it's still the same thing stands.
No, wait, we can actually improve something if a is negative. We can actually look at say minus a. Yeah. If a is negative, we can look at this as well. Because both of the roots must we have absolute value less than 2. So you can do this. And by the exact same way, if minus a is greater than 3, you can get a contradiction. So this is true. Okay, right now it's like not the part of the problem, and like assume you can just do this or an exercise to finish this at home. I'll be like making your
Okay, so
homework.
is like A from -2 to 2 and B equals 1, all the this answer of this case, or there
That is
will be
something
some.
I want to say. Now you'll get some inequality, right? Now you get some range of a, some possible values of a. As always, you must check.
Okay.
There might be some values which might fail as well. So you must check that they work. Okay?
So we'll have to check every single A in this range with plus minus.
It's not much, right? Like it's like half of the things would be stupid and like dumb. Like a is equal to this or this. Now 0 is already done. You get the polynomial x squared plus 1. Done. X squared plus or minus x plus 1. Like this directly works. You can just take the polynomial p to be like 1. The only issue is something like this. This you have to use something. It works, believe me.
It's
Exercise.
just x minus 1 square or x
Yes.
plus 1.
Yeah, exactly. If you have something like, yeah, you can just make it work. Similar case with b minus 1. Do it on your own. Okay. Not the main part of the problem. The main part of the problem was this thing. This inequality. I can
I'm actually curious. Like, could we have used beta there? Like, the other root is just 1 by alpha, or
right.
a minus alpha.
We can probably do that to improve our things, and that might help because we can directly assume one of the roots has absolute value 1 and greater than 1. No? Yeah, that might help. It's also a nice idea. Do we need to construct a value of p of x? Yes, you need to construct a value of p of x. That is only when it's a valid solution. So whenever you get a solution, always check it. Like just always check it. Okay, anyways, the main part of this problem was this inequality. There is a very nice motivation is that historical as a complex number. Okay, the issue is like I can't do entire polynomials in a class. So I decided to look at the roots idea, and this is a very common idea. And complex numbers, so you can take it as a constant of complex numbers. Whatever. This bound is the main thing. Anyways. Okay, enough chat. The issue, like another motivation I try to repeat it, is something like 2 can't be a root. So you don't expect large numbers to be a root. And you isolate the biggest term, apply that to triangle inequality. Keep this idea in mind. I don't think we have a lot of time, but we'll do another problem, which hopefully you might like more. So let R be a real number. A monic polynomial is R good. Again, absolute value or at most R. So all of its roots have absolute value at most R. And primordial is some fancy name. Now its coefficients have absolute value at most R. Okay? So don't get confused. The first thing says something about the roots. Would you summarize the problem again? Yeah, sure. I'll summarize it. So there's some division thing which this part I'll just not exactly do it because that is correct. Okay. So what we wanted was integers a, b, so that x squared plus ax plus b times some integer polynomial is a very peculiar polynomial which has all its coefficients as 1 and minus 1. So what we did was first of all put x equal to 0 or compare the constant terms to get that b must be plus or minus 1. That was the first part. The second part was we looked at roots. So if we take a root of x squared plus ax plus b, let me go ahead. X squared plus ax plus b. If we take any root alpha of this, we put it in, this guy goes to 0. So this must be 0. And just because that's a very peculiar polynomial, it's a very peculiar polynomial. So with very nice restrictions, a lot of restriction on its roots. And the reason we want to look at its roots is because if you look at 2 can never be a root of this polynomial. Because 2 to the n is much bigger than any of its smaller powers. And any plus or minus 1 linear combination can actually never make that.
I think 2 to the n is just exactly equal.
No, right? Like the sum of previous things is like, okay, so 2 to the n is like exact point where it fails, is what you mean, I guess.
No, 2 to the n is equal to 2 to the n minus 1 plus 2 to the n minus 1 so on till 1. This is equal.
No, they're not equal.
You can just check it once.
Yeah. 4 is greater than 2 plus 1.
Oh no. Okay, it's like
there's
1. I guess.
Yeah, it's like off by 1, but yeah.
By off by 1, yeah.
So basically, yeah, we found it off by 1. So we expect that large numbers cannot be a root. So we do this massive chain of inequalities. We isolate the biggest term. We have something remaining. And now we look at absolute values. Because inequalities do not exist in complex numbers. And we are not sure if alpha is a real number or complex number. So we have a very nice get around with it. We just throw absolute value on them. And absolute values are very nice. They are like some triangle inequality and very nice multiplication with them. We do some stuff, and in the end, we get some inequality like this. It is very similar to the issue we had for 2. Like absolute value of alpha to the n is less than the sum of the previous powers of alpha. And we showed that this is not possible if the absolute value is bigger than 2. It is another some polynomial stupid algebra. So all roots of x squared plus ax plus b must have absolute value less than 2. And because it's quadratic polynomial, you know how to solve quadratics. We solve a quadratic, do more boring algebra, get some inequality, check it works. Not the main part of the solution. The main part of the solution was looking at roots. Is the idea of the solution and summary of the solution clear? Or are there any more parts which need something more?
Okay, how can a polynomial with complex coefficients have multiples? Like divisors.
Why not?
Oh, like
X plus 1 times x plus I is a polynomial which has x plus 1 as its divisor. Or something like something worse if you want to look at. X cubed minus 1 has x plus omega as its divisor, where omega is the cube root of unity. X minus omega.
But
So these are some examples of complex coefficients. Okay, if you really are uncomfortable with complex coefficients, don't need to worry, look at them as normal numbers, but you don't have inequalities on them, and whenever you're working, just throw in the absolutes. Let's look at that like that. Okay. I don't think we have a lot of time. I really want to do part B. So, and part 1 is nice motivation about it. So, let's start with part 1. Any ideas about part 1?
similar to that last problem we did, right?
This statement is similar, yes, indeed.
No. The part
So-
1 is similar. We had at
Yeah.
most 2 we had at most 2 there, and here we have at most 1. But no, it's like
Yeah, part 1. Both parts are basically like characterizing something, you know. But whatever. Let's try to solve part 1 as its own. So if you have some polynomial like x minus alpha, where absolute value of alpha is at most 1, this works, right? This has a multiple x minus alpha, and this is primordial. Fine. But now if you have something like x minus alpha times x minus beta, with both alpha and beta have absolute value at most 1. What happens in this is that this would look something like this. Right? This guy has absolute value at most 1. Product of two numbers less than 1 plus than 1. But this guy might have a bigger absolute value. You know? So we somehow need to make alpha and beta, like the roots have super small absolute value. Not the roots, you cannot change the roots having absolute value. You want to make this thing really, really small, right? Does the idea make sense? Like basically, if we look at something like Yeah, is someone saying something?
No, the idea makes sense. I was actually talking about.
Ah, fine, fine. Like something like this. And if A and B are very, very small, like absolute value of A and absolute value of B are very small, we can actually force this works, right? This polynomial just works. Does this make sense? I think it doesn't. So what I mean by very small is that absolute value of A plus B, if we know this inequality is true. But if we just look at the inequality absolute value of A at most one, this just gives this bound this. And there are examples for this is bigger than. But what we want is this guy right here to be at most one. So what we try to find is that absolute value of A and B are very small, say less than 1/2. Then we can actually say that this is also less than. So does it make sense, like what we're trying to do?
Yeah, now it makes sense.
Great, great, great. So we want to make these guys very, very small, right? Very, very small. But we also want like alpha to be a root. How do we do this?
I think we can construct a polynomial just like x to the n minus alpha to the n, because x minus alpha divides
Exactly.
it.
That is a brilliant idea, and that is the main idea. So what we look at is x minus alpha divides this. And we have, this is also true. N is any integer. The reason this is very good is because now this product has alpha and beta as its roots. And it looks something like this, right? Y minus A times Y minus B. And we force A and B to have very, very small absolute values. So we want alpha to the n to have very, very small absolute value. And if absolute value of alpha is less than 1, we can actually do this. Right? Because exponents of something less than 1 go really, really small. Like, look at half to the n goes very, very small. Right? Great. So, assume we are done with this part. But like, there is some issue. We actually had one good polynomials with absolute value at most 1. What happens is absolute value of alpha is 1. What if absolute value of alpha is 1? What do we do now?
Can I please see the question again?
Yeah, sure.
Thank you.
So I actually want to do part B more, so we like skip this for the later thing. Let's try to do part B. Okay. So for r greater than 1, we want to find an r good polynomial that doesn't have a primordial multiple. So we want to find a polynomial which has roots at most r, all of the absolute value of all roots at most r, such that there does not exist some polynomial q which is primordial. Fine. So q would look something like x to the n plus blah blah blah. All of these coefficients have absolute value at least 1. So how do we do this? Like, this is what I mainly wanted to do. The first part, we can try it later. We don't have much time. So any ideas? But I guess I'll just tell it because we have much time. That is again looking at roots because yeah, we are given a root. Let's try to do something. So if alpha is the root of p and assume a contradiction, we want q to have something. Okay, q has the root alpha as well, right? Alpha is the root of q as well. So let me actually write carefully. Similar notation to the previous problem, but this time we have something different. So we have alpha to the n plus kn minus 1, alpha to the n minus 1, so alpha c1. So this is equal to 0. What do we do now? Does anyone have any ideas now?
Take all the CIs to be 1 and
So,
then
like,
using the
yeah, go ahead.
like in the previous problem we had shown that modulus of r whole to the power n is less than equal to r to the power n minus 1 by r minus 1, that thing. And since r is greater than 1, that would be less than r to the power n minus 1. Means something along that lines.
Yes, precisely. Precisely. That is exactly what we will do. We will again isolate this guy. And throw absolute values. Because we want an inequality and we need to use this being something. Anyways, absolute value, triangle inequality, exactly the same way as we did with the previous problem. Then use multiplication. And then we use that each of these absolute value of Ci is at most 1. So we get this again. This is exactly the same as you got the previous time. So if mod alpha is bigger than 2, this is false. This means so the polynomials of the form x minus alpha for mod alpha bigger than 2 do not have a primordial multiple, right?
Oh yes.
So we are done with like a lot of numbers. So basically if r is at least 2 is actually equality can hold. If r is at least 2, we are done. So what we want is r less than 2. Not bad. So the issue is directly the polynomial x minus alpha is gonna fail. So how can we improve this? We want again alpha to be big. Like not alpha to be big, but okay, I'll actually say some motivation. The reason something like this was failing for large absolute value of alpha is because the alpha term is the absolute value of alpha is like very big, right? So if there were a polynomial that multiplied to x minus alpha and gave a primordial polynomial, so it actually kind of like stabilized the term of alpha into something very small. Does that make sense? But
Could you please
the issue is
repeat?
alpha. Yeah, I'll repeat that. So what was happening in this case, I'll just explain why this case you expect it to fail, or why you expect the problem to be true. Is if you look at something out of the form x minus alpha, with alpha having a big absolute value, and x has a like the coefficient of x is just 1, and alpha has a comparatively big absolute value to 1, and it had a primordial multiple. So it has a polynomial which multiplied to x minus alpha and resulted in primordial. So the issue was that what that polynomial should do is somehow balance out this big alpha coefficient into something small, right? It must have some very nice polynomial which actually balances out. So alpha is big right now. It must throw a negative number to put it down. But if we throw that negative number to put it down, it must actually cause some other coefficient to go big. and then put that alpha to go down, and then big, and down. Does it make sense? Like, what is going on? What issue is actually going? Like, what is the main issue that's going through?
Yes.
So now our aim is to actually construct a polynomial which is like a big absolute value for a coefficient, but small. It's a monic, like something like that, with alpha having a root. So you want something like some polynomial which is like big absolute value of these coefficients, and it's something like x or something. X to the n. Any ideas? And not also damaging a lot of roots. As in like getting big roots. You also want the roots to be small absolute value. You don't have a lot of time. But we have actually looked at this polynomial before. It's just this. Now, because we know r is greater than 1 in this case, and we want an alpha, which is absolute value at most r, we force this to be greater than 1 because we can do that. And now this guy's absolute value will explode. We can make it as large as we want, right? And all of these roots actually have absolute value alpha. Assume this if you don't know this, if you know some complex numbers and roots of infinity, this is fine. Good. And this is true as well. So this polynomial, absolute value 1, this is huge. So you don't expect this to work. Right? Now, assume it works. Let's try to find a contradiction. So this divides some primordial q of x, which is again the n is not the same. I'll use an m here. C naught. How do we do this now? Well, someone said a very nice idea in the beginning, is that we try to reduce powers of n smaller. That is, if we have something like x to the n plus 1, we can actually write this as x, right? Okay, not exactly x times alpha to the n. When we're dividing by this, that's like, okay, look at this as a number now. Look at this as a number. And in some sense, this equality holds true, right? In some sense. Does this make sense? When you're looking in some, does this make sense?
Yes, somewhat.
Yeah, like, okay, don't think this is an actual fact. If you write this somewhere, it's like wrong, but technically wrong, intuitively right. And right now, just care about intuition. We don't have much time. So intuitively, does this make sense? I hope it does. So basically what your idea is, you can reduce any exponent up here, anything, to something like alpha to the something times x to the something less than n, right? Like say this is like x to the 5n plus 10, we can write it as alpha to the 5n x to 10, right? Okay, this equality is like just because you're working in this division, you know, you're just dividing terms. Does it make sense?
Yeah, it is kind of like we do in factor theorem, like
Exactly. Yeah. That's basically what I want you to do. This is not completely correct, like it's not technically correct, but intuitively that's what we care about right now. Okay, great. Why do we want this? Is now, if you look at, so everything now looks like something like this, right? You have some constant term, which is alpha in it. Some, let's call this a0. Then you have some a1 x, a2 x squared, so until an minus 1 x to the n minus 1. Correct? This is the remainder, right? That's what we're doing. We're trying to get the remainder. Does it make sense? And this must be 0, right? Because the remainder must be 0. We're assuming the polynomial divides it.
Yes.
Which means all of these coefficients actually must be 0. Correct? This is great stuff. So now we have a lot of equations with alpha as a root. Like, okay, not alpha as a root right now. With alpha, which are 0. Correct?
Yes.
Brilliant, brilliant. Now what our idea is, now what we want is like some equation which has some alpha to the n term here, plus some, not exactly m, some alpha to the k term here, plus some blah blah, we don't really care about that. And then we want to isolate this term and then do our inequalities, right? What we really require is this thing to be 1. Or a fixed number, not something like very small or coefficient, don't know about it. We want this to be 1. So we look at this back. We know some guy is 1 right here, right? Some person is 1 here. So, and all of these guys are like x to the m must be reduced to one of these a1, a2 or an minus 1, right? So one of those guys must have x to the m in there, which means something like this exists, alpha to the k exists, and like with coefficient 1. Correct? Correct, right?
Yes.
More importantly, when you're reducing, notice the terms alpha to the n are always appearing. Alpha never appears. Every term that you'll reduce will have alpha to the n, right? Every term that you have actually has an alpha to the n and not an alpha, right? Because if you're reducing something like x to the some k, you're actually writing as x to the n times x to the k minus n, and then writing this as alpha to the n and then x to the k minus n, and then going ahead and reducing this. So every term actually has an alpha to the n in it. So you get some polynomial, something like this, alpha to the kn plus some constant di, t k minus 1, alpha to the k minus 1n, and so on, right? Is this part fine? This equal to 0. And all of these di's are actually coefficients of the q. Okay, I think this is going very fast right now. Sorry, this is going fast. I'm already exceeded time. But basically, I'll just finish it right around from here. You look at this, call alpha to the n as some beta. This is beta to the k, and so on till d naught equal to 0. This is a primordial polynomial with beta as a root. So absolute value of beta cannot be greater than 2. But we can choose an n so that it gets arbitrarily large. Okay. I hope this didn't went too fast. And I think that's the end. So if people got it or are fine with it, we can now leave. And if people want to know more about it and have questions, feel free to ask right now. And if you don't mind slightly extending it too much.
Could you please repeat the last part? Like where we
Yes.
got all the coefficients were 0. I got till there. But what about after
Yeah,
that?
yeah, I'll do that. So, okay, when we are reducing this thing, do you agree that every coefficient will have an alpha to the class is over, by the way, so if people actually want to leave, I won't be doing any new problem, I'll just be explaining this. So when you're reducing, do you get this that each term would have an alpha to the n? Like everything has an alpha to the n in it.
Yes, I understood that.
Great. So now you got everything must be 0. Now our aim is to repeat something we did in the starting, right? Because each of these A0, A1 are actually something in alpha, right? Something of the form, something Ci alpha to the I, right? Not the same Ci, some different Ci. This is equal to 0.
Yes.
1 second. Stop recording. I think you can stop recording. Anyways, so each of